Okay, so the last of the lectures on acid-base chemistry will sort of again look at the idea of the applications of acid-base. And this is sort of preliminary because when we get into curved arrow mechanisms, which is the next big topic, we will see how acid-base becomes a really important feature. But where we ended last day was looking at how we would predict the results of an acid-base reaction. And so let's just go ahead and do some examples. So what if I ask the question, what would happen if I reacted, say, hydroxide with methane? Okay, so I'm treating the hydroxide ion with methane. So the question is, what is the result of that reaction? Well, I'm going to say, okay, so this looks like an acid-base reaction, right? Because in fact, quite frankly, electron pair transfer reactions are acid-base reactions, okay? So I'm going to ask the question, well, fine, what role could the hydroxide play? What role could the methane play? And the answer is, well, hydroxide has an H, and therefore, technically, the hydroxide could be a proton donor. So functionally, hydroxide could function as an acid and donate a proton to the methane. But the problem is, our definition of a base is an electron pair donor, and we know full well that the only electron pairs that are donatable are those that are lone pairs and or pi pairs. That sigma pairs are non-nucleophilic, they're also non-basic. So if I look at methane, all methane has are C8 would be CH single bonds. Methane therefore only has sigma bonds. Methane is not basic. So if methane is not basic, it cannot compel hydroxide to function as an acid. So even though hydroxide has proton, it cannot donate the proton to the methane because the methane does not have the tools vis-a-vis a lone pair of electrons or a pi pair of electrons to act as a base. Therefore, of my options, I'm going to say, well, the only possibility is hydroxide will function as a base, and methane then can function as an acid. And that's reasonable, right? Hydroxide certainly has 3 lone pairs of electrons and a negative charge, and therefore, as a result, it would be our definition of a base, right? It's electron-rich species. Methane certainly has H bound to carbon, and therefore methane could potentially function as an acid, as a proton donor. So if any reaction is going to happen, it would be that a hydroxide would use its electron pair to deprotonate the methane. The 2 electrons in the CH bond will get dumped onto the carbon, and I will end up with HOH, in other words, water, and CH3 minus. Now, I should not have to tell you, right, it should not be an issue at this stage, why the C has a minus charge. Okay? Obviously, it's gaining a lone pair of electrons, so if I were to do Lewis counting, it would have 5 electrons that belong to it, and hence a minus charge. Or I can make the usual argument that the carbon here is neutral, having invested 1 electron in this bond. It's getting back that electron plus H's electron, hence the minus charge. Now, if I ask the question, is hydroxide a stronger base than methane? The answer is yes. Right? Because hydroxide has lone pairs, methane does not. Okay? But that question is irrelevant to the issue of whether the reaction goes or not. I am not interested in comparing this species to that species. I am interested in comparing the base to the conjugate base, the acid to the conjugate acid. So what does hydroxide form on protonation? And the answer is it forms water. So water then is my conjugate acid. Again, the species formed on protonation of the base is the conjugate acid. The species formed on deprotonation of the acid is the conjugate base. So the question I have to ask is hydroxide a stronger or weaker base than methide or methanide? And is methane a stronger or weaker acid than water? Asking the question about whether hydroxide is a stronger base than methane or whether methane is a stronger acid than hydroxide is an irrelevant question. The only question you ask is, you compare base to base. Base to conjugate base, acid to conjugate acid. So let's see. Of the two, OH minus, right? OH minus and CH3 minus. Which of these two species is the stronger base? So I'm going to ask myself, what makes a base? What is a base? The answer is a base is an electron pair donor. When will I be a strong base? And the answer is when I'm a reactive base, right? When I'm not a stable base. Why will I be unstable? I will be unstable because having the electron density is destabilizing. So in other words, the question is which of the species, C minus or O minus, is more desperate to get rid of electron density? Well, look, O is electronegative, right? And therefore the oxygen atom spends its life drawing electrons towards itself. So I gotta believe that O must be comfortable with electron density. Carbon is not electronegative, and therefore I have to believe that putting a minus charge on carbon significantly destabilizes carbon, and therefore of the two atoms, carbon should be the more desperate to get rid of electron density. In other words, methide should be a stronger base than hydroxide. Now you notice I'm comparing O to C, and these are periodic partners, and therefore any decision will be based upon electronegativity. So since O is more electronegative than carbon, it will be more adept at supporting a negative charge, and as a result it will be more stable. If it is more stable, it is less reactive. If it is less reactive, it is weaker. And therefore hydroxide is a weaker base than methanide. Therefore this reaction cannot occur as written. I could have done the argument the other way, right? So here I compared base to base. I could just as easily have compared water to methane. In other words, I could have done an acid to acid comparison. So let's do that one. I'm going to ask which of these species, water or methane, is a stronger acid. Well, for heaven's sake, the issue is O and C are periodic partners. Therefore, the issue comes down to a difference in electronegativity. So O is much more electronegative than H, and therefore the OH bond is going to have a significant polarity on it. H has the same electronegativity as carbon. In other words, carbon being much less electronegative than O means that its ability to polarize the CH bond is much less, and to all intents and purposes, there's no dipole on the oxygen, on the hydrogen. So it means the H of water is more protonic than is the H of methane, in which case water is a stronger acid than methane, and the reaction cannot go as written because the weaker acid gives rise to the stronger acid. Okay? Now you would notice two things. One, hydroxide is a weaker base than methanide. So I'm going to say weak. Right? And this would be, well, let's say weak. Also in my analysis, methane is a weaker acid than water. So the two weaks and the two strongs are on the same side. The weaks are on the same side. The strongs are on the same side. And it must be that way, right? Also, you notice that the argument we used to show that hydroxide is a weaker base than methanide was an electronegativity issue based on the fact that C and H are in the same period. That is exactly the same argument we use to account for why water is a stronger acid than methanide. It is the fact that O is more electronegative than C, as these are periodic partners. Right? So in other words, we're taking exactly the same argument, maybe turning it around a little bit, and we're getting to our answer. Now, another important point to note is, if I would ask the question, is hydroxide a stronger base than methane? The answer is yes. Hydroxide is a stronger base than methane. But that is an irrelevant question, as illustrated here, because we're not going to get chemistry. Right? Even though hydroxide is a stronger base than methane, we don't get a reaction because it has nothing to do with the relative strength of hydroxide and methane as acids or bases. It has everything to do with the relative strength of hydroxide and methanide, and methane and water. The other point to make is, so this reaction does not go, which means I've mixed two things and nothing happened. It is perfectly legal to mix two reagents and have nothing happen. Chemistry does not happen because you mix stuff. Chemistry happens for a reason. And mixing stuff is not a reason. Okay? Let's do another one. So what if we had the reaction between, for example, let's say NH2 minus, okay, and say H2O. Right? What would happen if I mix NH2 minus with H2O? Right? Would I get a reaction? Well, I'm going to ask the question: what role would NH2 minus play? What role could water play? Now, in the previous example, it was really a done deal because the methane could not possibly function as a base. Why? Why not? Because it had no lone pairs or pi pairs. So if anything was going to happen, hydroxide would have to be the base, this would have to be the acid. Right? So there was no issue there. Okay? In this case, it's a little more complicated because in the amide ion, I have H attached to N, so therefore this can function as an acid. But I also have lone pairs of electrons on the nitrogen. And therefore, this amide ion could potentially function as a proton donor, right? Because it has H attached to N. And really as a base, because it has lone pairs of electrons. And in fact, it's got a negative charge. So this could be either an acid or a base. Similarly, I have H bound to O, and so water can function as an acid in this context. But on the O, there are two lone pairs. So technically, the water can also function as a base. So all things being considered, I should say, well, look, there are two options, well, really three options. Either this is my base, that's my acid, right? This is the base, and this is the acid, and I get chemistry. Or this is the acid, that's the base, and I get chemistry, or we get no reaction. Now, rather than go through both options, I can immediately take out that option. And the reason is, let's think about it. An acid is a proton donor, at least in the context of these proton transfers. Which means the species has to be willing to give up H+. NH2 minus is negative. Its ability to give up a positively charged species is going to be severely compromised because the positively charged species would be leaving an entity that is negative. And if it would depart, it would leave a species that is 2 minus. So the ability to pull away H+ from something negative, I mean, that's going to be extremely hard to do. So I gotta think that of the two species, NH2 minus can't be the proton donor. In which case, the more likely option, the one I'm going to entertain, is that NH2 minus functions as the base, and this is going to act as the acid. Now, having done that, that does not mean there's going to be a reaction, right? Because that's what I did earlier. I argued that in the previous case, what the heck? I argued in the previous case that hydroxide was the likely base and that methane was the likely acid. That didn't mean I got reaction. What I had to do is to generate the conjugate acid and conjugate base pair and compare base-base, acid-acid, right? So I'm going to do the same thing here, not because I've identified the likely role of NH2 minus and the likely role of water. Does that mean that I'm going to get a reaction? I have to carry it through and say, fine, if NH2 minus is the base, what does it do? And the answer is, and I'm going to redraw this slightly, right, so we can see the curved arrow. If anything were to happen, and I'm not saying anything does, the NH2 minus would use its lone pair of electrons. It would steal the H, right, that's H plus from the water, and generate the ammonia molecule and hydroxide, right? This would be the conjugate acid. This would be the conjugate base. Does the reaction go? Well, it depends. Is water a stronger or weaker acid than ammonia? Or is the amide ion a stronger or weaker base than hydroxide? Well, again, N and O are periodic partners. So I'm going to ask the question. Which of these two species, right, is the stronger base. And what I'm really asking is, what is a base? A base is an electron pair donor. When will I donate electron pairs? And the answer is when the species having the electron pair, or in this case a minus charge, is uncomfortable with it, when it's more uncomfortable. And since N and O are periodic, the issue is going to come down to electronegativity. So O is more electronegative than N. They're both electronegative, but O is more electronegative than N, which means O minus should be a more stable species than is N minus, right? Because the O being more electronegative should be more comfortable with electron density. So there should be a greater need for the N to give up electron density than for the O. In other words, NH2 minus should be a stronger base than OH minus. In which case, strong gives rise to weak, and the reaction should go as written. Having done that, I'm finished with my answer. I know the reaction goes. But I could have attacked this from the other end. I could have said, well, let's compare acid to acid. And this is the last time I'm going to do both, because doing both is really not necessary. Let's compare acid to acid. Which of the two is the stronger acid? Well, again, N and O are periodic partners. And the issue is going to come down to electronegativity. Because O is more electronegative than N, the dipole on the OH bond is going to be greater than the dipole on the NH bond, right? Right? In other words, the N pulls electrons less effectively from the H than does the O, in which case the H in water is more protonic than is the H in ammonia. Hence, the strong gives rise to the weak, and the reaction goes as written. So it's another illustration that I'm using really the same argument, maybe turned around a little bit, to account for the differences in the acidities and in basicities. Okay, let's do a slightly different one. Let's look at the relative strengths of a couple of acids. I'm going to take H, OCl, HOCl. In fact, I'm going to, slightly different example. Let's look at H2S, HSO3, and H2SO4. Crikey. H2SO4. So this is H2S, hydrogen sulfide, H2SO3, sulfurous acid, and H2SO4, sulfuric acid. And I'm asking which of these is the strongest acid, or to rank these in terms of increasing Ka values. Well, again, what are the factors affecting acid strength? And the answer is, well, it comes down to the solvent, which I'm going to assume is the same, the HX bond. So how are S and O related? Well, the answer is in the same group, so the HS bond is longer than the HO bond. So based upon the length of the HS bond, or the greater length of the HS bond, I would say, well, maybe H2S is a stronger acid than these. And certainly that would have been true if I were comparing H2S against H2O, right? That would be where the argument would end, that H2S is a stronger acid than H2O, which in fact it is. But if you look, the structure of H2S and these other compounds is quite different. So what I'm going to do then is I'm going to look at the species formed upon deprotonation. So when H2S is deprotonated, I make SH minus. And the negative charge here is on a fairly large sulfur atom, which is a minus charge on it. But when I deprotonate the sulfurous acid, oh, good Lord, this is not the right structure. This is H2SO3, I'm sorry. So H2SO3. When I deprotonate the sulfurous acid, although the minus charge is on a smaller oxygen, I do have the option of resonance. And resonance here gives rise to not just one resonance form, but two resonance forms that are equivalent. And remember we mentioned one, that the more resonance forms I draw, the more stable you are, and two, if the resonance forms are equivalent, right, then I drew the hybrid, but the other resonance form to this would look like this, right? It's OS, double bond, O single bond, OH. And this and that are equivalent. This is the hybrid. When you can draw equivalent resonance forms, you get a bonus in stability. And in fact, the more equivalent resonance forms you can draw, the greater is that stability. And that's what happens in the sulfuric acid. If I look at sulfuric acid, at the conjugate base, which is bisulfate, or hydrogen sulfate, right? Obviously, I've got a minus charge in the O, and I can draw this resonance form, right? So that's O double bond S, single bond O minus, double bond O, OH, and I can draw a third resonance form, right, which gives rise to O, double bond S, double bond O, single bond O minus, OH. So in reality, what I've done is I have smeared my minus charge over 3 oxygens, right, like so. So I have dispersed the charge more effectively. Put another way, I have 3 electronegative atoms bearing the burden of the minus charge. And therefore this conjugate base is going to be more stable than the one from sulfurous acid, which will be more stable than the one from H2S, right? So in general, if I'm comparing HX and HXO and HXO2 and HXO3, the acid strength goes up in that direction, okay? And that's an issue of resonance versus just induction. The last point we make about acid-base chemistry is that I can use acid-base chemistry to my advantage in something called DT labeling. So it becomes important in organic chemistry, especially in mechanistic organic chemistry, and certainly also in biochemistry, that's technically mechanistic biochemistry, to swap hydrogens in a molecule with either deuterium or with tritium, which are the other isotopes of hydrogen. So again, just to remind you, each comes in 3 flavors, which is protium, deuterium, and tritium. And we call H21 deuterium will give the symbol D, H31 tritium give the symbol T, and protium has the symbol H. Okay, so those are my isotopes. So let's say, for example, I had a, let's give you an example. So let's say I'm an alien from a different planet, and I want to figure out, I believe that if I take glucose, right, that organisms take in glucose and they do metabolism, and they convert glucose into carbon dioxide and water, okay? So organisms put in oxygen, and they convert the glucose into carbon dioxide and water. That's my theory, right? My hypothesis. How could I test that? And one way of testing it is to say, well, fine, I'm going to feed that organism I'm going to control its diet. So the only source of glucose that it finds has D rather than H. And if I find that under normal metabolic conditions, it generates D2O, then it must mean that the D came from the glucose. I could have just as easily fed the organism labeled carbons. I can use carbon-13, for example, and if it made radio-labeled carbon dioxide, that would also confirm that that is the source of the carbon in carbon dioxide. So labeling is a very useful technique for following pathways, okay? So let's say I had this compound. Let's say I had propine, and I wanted to convert propine into, say 1-tritiopropine. How would I do that? And the answer is, I would take advantage of acid-base chemistry. How would I do that? I would take the alkyne, it's a terminal alkyne, and they're modestly acidic. If I treat a terminal alkyne with NH2 minus, or with, for example, CH3 minus, what I would get would be the corresponding acetylate. This is an acetylate, right? And this is a simple acid-base reaction. So it would be the alkyne, for example, plus NH2 minus, right? Bang, bang, would give rise to the acetylate plus NH3. Or the alkyne plus CH3 minus, which I'm just going to write as Me minus, right? Me minus would give rise to the acetylate and methane. And again, this is simple acid-base chemistry. The reason this goes is because the alkyne is a stronger acid than the alkane, sp hybridized, sp3 hybridized, because the methanide is a stronger base than the acetylate, sp3 hybridized, sp hybridized, right? And the argument here, of course, is that because the carbon is sp3 hybridized, that the lone pair of electrons, right, is further away from the carbon's nucleus than is that lone pair of electrons. If you're further away, then you're less stable. Therefore, you're a stronger base, right, than here. And then with the alkyne and the ammonia, the issue is that, look, even though N is ordinarily more electronegative than carbon, I'm not being fair here because I'm comparing sp hybridized carbon with sp3 hybridized nitrogen. And the deal is, if you look at an electronegativity profile for atoms, right? So here is, for example, electronegativity, and here is, let's say, sp3, sp2, and sp. If I take carbon, the electronegativity of an atom increases as we increase the amount of S character, right? So this would be my plot of electronegativity for carbon. If I run a similar plot for the electronegativity of nitrogen, well, sp3 hybridized nitrogen is more electronegative than sp3 hybridized carbon, and will behave. And certainly sp2 hybridized nitrogen is more electronegative than sp2 hybridized carbon, and sp hybridized nitrogen is more electronegative than sp hybridized carbon, and this is absolutely true, right? But if I look at, oh, well, this is a bit generous than in my diagram. Let me just fix that a little bit. All right, so this is sp hybridized nitrogen, sp2 hybridized carbon. So stop. sp2 hybridized carbon, sp hybridized nitrogen. Right. So hybridization state for hybridization state, sp hybridized nitrogen is more electronegative than sp3 hybridized carbon. sp2 hybridized nitrogen is more electronegative than sp2 hybridized carbon, and so on and so on and so on. But if I look at the profile, what I find is that sp hybridized carbon is actually more electronegative than sp3 hybridized nitrogen. And the reason this happens is because C and N are right next to each other in the periodic table. Okay? So it turns out exactly the same thing happens with N and O. Right? If I look at N and O, I'm just going to set it up. If I look at N and O, here would be sp3 hybridized O, sp2 hybridized O, sp hybridized oxygen. Right? In a similar fashion, sp hybridized N is more electronegative than sp3 hybridized O. Okay? But there is no hybridization state of carbon that is more electronegative than any hybridization state of oxygen. Right? So when the atoms are next to each other in the periodic table, the sp hybridized version of the atom to the left is more electronegative than the sp3 hybridized version of the atom to its immediate right. Okay? Anyway, so this reaction goes as well. So my question again is, how do we get the labels on? So going back to the first part, the alkyne reacts with NH2 minus or with CH3 minus, gives rise to the acetylate, right? That's the acid-base reaction. And I'm going to lose in the process ammonia. Then I can take advantage of a second acid-base reaction and treat the acetylide with D2O or T2O. So if I use T2O, which is the tritium equivalent of water, I'll get a second acid-base reaction that will lose what essentially is hydroxide, or it's called tritoxide, and I will make the 1-tritio compound. And that's another simple acid-base reaction. This will go because the acetylide is a stronger base than the hydroxide, or, if you will, T2O, water, is a stronger acid than the alkyne. So the reaction is going to go. So a pair of acid-base reactions is very effective in generating labels. So I could have used D2O here instead of T2O and have made the 1-deuterio compound. Finally, another way of introducing labels is to do what's called zinc acid reduction. Alright, and if I, for example, take a haloalkane, right, where X is a halogen, and I treat it with zinc and H+, what I'll get is RH plus zinc 2+ plus the halide ion. Right, that's the standard reaction. So this is a way of reducing, because I'm going from the alcohol level down to the alkane level. And of course, zinc is a metal. Metals are reducing agents. So the zinc has lost 2 electrons, right, to make zinc 2+. So that's a reduction. That's a reducing agent. The alkane, the haloalkane, has gained 2 electrons because it's lost 1 bond to a heteroatom. Well, there's no reason why it has to be H+. If I use zinc and D3O+, and of course H+ is really H3O+, right? If I use zinc and D3O+, I'll make RD. If I use zinc and T3O+, right, in other words, TCl in T2O, or TCl in or T2SO4 in T2O, I'll make RT. Right? So I could introduce labels into organic compounds either by a simple acid-base type reaction, as we did in the previous case, right? Or I can do it in this fashion. Okay? So in general, I can introduce labels either from R- and say D2O, or, right, to make RD, or I can treat RCl, right, or RBr with zinc and D3O+. And both of these are ways of generating RD. We'll see in a while that there's a way of converting RCl into R- and then doing chemistry. Okay, that will end our third and final lecture on acid-base chemistry. Thank you.